Okay, so as Marion indicated, my name is Karen Wright, and I work at Idaho National Laboratory in the United States. And I'm part of a post-irradiation examination group. So I work performing EPMA analysis on generally irradiated nuclear fuels. So I'm going to talk a little bit about some of the challenges that we encounter in this process. And at the end, I have a few slides showing some more recent research. So people who do this work know that there are abundant challenges. Of course, there's the obvious one of radioactivity. That makes the samples really difficult to handle. We need specialized equipment to do so. There's generally a lack of quality standards for our analyses. And when we measure actinides, we're using M lines, and there are numerous overlaps with these lines. The mass absorption coefficients for some emitter absorber pairs are poorly constrained, and they negatively impact our analysis accuracy. And one thing that I have discovered fairly recently is that the existing Thyro-Z corrections don't appear to work well for some of the fuel types that I've been examining. So to begin with, if we have a radioactive sample and we put it in an instrument and we have no beam, what we'll see is as the energy of the nuclear radioactivity increases, the background intensity increases. This is intuitive, but it also presents a problem that we need to solve. So here you can see it a little bit more explicitly, where if you notice, and I'll focus here on neodymium L alpha, and this is distance in microns. It's not particularly readable, but this is 0 and this is 8,000, and these are counts, and this is simply moving a radioactive an irradiated MOX sample, a mixed oxide sample, to closer to and farther away from the detector. So here's moving in the X direction, and we could see the background here at perhaps 1500, and you get away from the detector and you're down at 400 or so. And the same thing is happening in the Y direction generally, but the shape of the background is different. And so that presents a whole set of problems in terms of getting stable background so that we can get accurate analyses and good detection limits. So the way to do that is by having a shielded instrument. And so here's a sample, a radioactive sample with a 150 milliamp per hour field, gamma field at 30 centimeters. And without any shielding, what we have here is the wavelength in angstroms from 3 to 7, and a logarithmic scale for counts per second. And without any shielding, we can see that our background is here around 10 to the 3. Now, if we add shielding, we reduce that background by a factor of about 10. And then if we add electronic discrimination, and what is meant by that is to use your PHA in differential mode rather than integral, you can decrease your background by another factor of 10. So simply by using shielding and electronic discrimination, you can improve your background by a factor of about 100. And so here's a schematic of the instrument that we have showing shielding in these shaded areas. and so it makes for a very heavy instrument because this shielding is made out of a tungsten alloy. And this is a fairly large cylindrical block that sits on the stage. And there's a cutout right here. And the sample shuttle slides into this cutout, and the surface of the sample is about level with the top of this shield, so that the sample is shielded on most of its sides except for the top and to a lesser extent the front. And there's an annular shielded ring around this area that helps reduce transmission of radiation laterally. And then finally, there's shielding in the spectrometer that reduces stray radiation incident upon the detector. And what we have over here is the photomultiplier tube and the scintillator, and they're both at or below the level of this shielding, so that preserves our imaging capability. So we have a complex set of infrastructure and equipment to deal with these samples, because for the most part, they can't be handled by hand. So here is where the operator sits. The electronics cabinet for the instrument is over here. The instrument itself is behind this window, and these walls are composed of 20 centimeters of steel. So the instrument is behind this window here, and here is a glove box that's actually attached to the instrument. And you use these, what are called remote manipulators, and they are robotic devices that control essentially a set of tongs that you can use to load your sample coder, put the glass over the coder and load your sample into a sample holder and put the sample holder on the shuttle and put it into the instrument. That's all done with these remote manipulators. So that means that it takes a fair amount of time to actually load your sample and deal with your sample logistics. So I mentioned that the M lines are, there are a lot of overlaps with these lines. And here's an example of a spectrum with the elements that we tend to look at in the actinides: americium, neptunium, plutonium, and uranium. And we're looking at this on this in a wave scan on the using a quartz 1011 crystal at 20 keV. And so we have the spectrometer position and counts per second. And you can see the various lines here. We have substantial overlaps here with neptunium M beta overlapping americium M alpha, plutonium M alpha overlapping uranium M beta, and smaller overlaps here: neptunium M gamma overlapping americium M beta, and uranium M gamma overlapping plutonium M beta. So these all need to be corrected. And this doesn't even take into account the fact that in between these peaks, there are peaks for various fission products. So it becomes a very challenging operation to find good backgrounds for these materials. So one of the tools that we use is this quartz 1011 crystal. And I think it's better than the PET for several reasons. First of all, if we consider uranium M alpha full width half maximum is 12 EV in this 25 keV scenario. And if we use the quartz, it's 9 EV, so it's a 25% improvement. And of course, you get a decrease in intensity, but I've not found that to be problematic. But you do get better peak separation, and what you don't see here are numerous fission products in between these other peaks of interest. And I've highlighted the peaks that I choose here in bold: uranium M alpha, neptunium M alpha, americium M alpha, and plutonium M beta. So one of the things that we want to do is we want to understand how our fission products move within a fuel sample, because that can tell us something about how well the fuel is performing and how well it would perform under, for example, an accident scenario. So in order to do that, we need to have good detection limits. And because of our elevated backgrounds, that's harder to achieve. Here we have an irradiated specimen in orange and an unirradiated specimen in blue. And here's current, and this is neodymium L alpha detection limits in weight percent, and the same with xenon L alpha. And you see at low current, there's almost a tenfold difference in the detection limit here between the fresh and the irradiated specimen. However, as you increase the current, you get close to convergence between the irradiated and the fresh specimens. So we commonly use these very high currents, 200, 250 nanoamps, so that we can achieve the lowest detection limit that we can with that kind of specimen. And I should say that that creates a different set of problems in that we then need to choose a fairly robust coating material for our non-conductive specimens, because we also use elevated counting times to increase precision. And I've found that aluminum and carbon degrade rapidly under high currents, and so I'm now using iridium. So some of our mass absorption coefficients are not particularly accurate, and I'm going to focus here on oxygen K alpha in uranium. And we've got three MACs here for that. We have a Farthing and Walker MAC, and that's a MAC that comes from the Institute for Transuranium Elements, and most of their MACs are from Heinrich tables, but then they have some extended actinide MACs, and this is one of those. So we see that that's 11,100. And at the other end, the NIST MAC is 7,500. And then here in the middle, and most recently, we have the MAC for Pummel and Lovett at 9,300. So if we take a sample analysis and try our different MACs on the oxygen in uranium, if we use the Farthing and Walker, our oxygen content's 11.7 weight percent. And if we use the NIST, it's 8.88. And if we use Pummel and Lovett, it's 9.96. So there's a huge discrepancy between these mass absorption coefficients, and it's really important that we get it right for certain fuel types. For example, if we're looking at oxide fuels, uranium or plutonium oxide, one of the parameters that we want to know is the oxygen to actinide ratio as it changes across the fuel radius. And if our oxygen values are really inaccurate, it's of no help whatsoever. So that's one of the things that we as a community need to work on. And Philip Pummel and Xavier Lovett's contribution has been really, really helpful to us. Next thing I'd like to show you is something that surprised me, I guess, when I started looking at it. And these are several available Phyro-Z corrections, and some of them are quite old. This Heinrich one, for example, is quite old. The Love Scott comes from the mid-80s, and the most recent one is the Pouchot and Pouchois, the PAP. And this is a really well documented algorithm, and it's the one that's most widely used by people in our community, and indeed, I think, by the geological community. However, if we look at an analysis here of uranium, plutonium, and zirconium, the uranium values are fairly close to one another, and the plutonium, again, fairly close. But there's a huge discrepancy here with zirconium content. And so it's instructive to back out some of the correction factors in these algorithms. And we can see for uranium, plutonium, and zirconium that the absorption corrections here, and here, that they're fairly large. And this is not surprising because we're using a fairly high overvoltage, 7 and 6 for uranium and plutonium respectively, and 11 for zirconium. And so you might say, well, why are you doing that? You're just exacerbating your absorption correction problems, which is true. But the sample density is around 14 grams per cubic centimeter. So in order to get good beam penetration, you have to use a high accelerating voltage. And so what's more concerning to me than the high general correction factor is the lack of agreement amongst them. And so for uranium, from the lowest to the highest, the difference is about 0.04. The same thing for plutonium, but for zirconium, it's more than double that. And so it's unclear to me, using the same mass absorption coefficients, how we're getting really different absorption correction factors for zirconium. And it really is important that we understand this. And so one of my future projects is going to be diving into these and understanding how these were initially modeled, tested, because some of them were designed really for oxide samples of low Z, some of them for binary metals, and so on. And it may end up being that some of these corrections are better for certain fuel types than others. We also have a general lack of quality standards, and this is particularly true with our actinides. One might think that using a metal is a good idea, and I had tried that, and it turns out that they oxidize really rapidly and can exhibit large volume changes, which makes them just flake apart and cause problems with contamination in your instrument, which you really don't, which you really want to try to avoid. So we can sinter oxide material, and that works pretty well, but we have to make sure that the temperature and atmosphere control is correct for the stoichiometry that we want to achieve, because these elements have numerous oxidation states. The second thing we have to consider is the half-life for some of these elements. So for example, if we were to choose the isotope plutonium-241, we have a half-life of 14 years, which is probably not what we really want, because then we have to keep reevaluating not only its changing peak concentration for the analyte of interest, but also the ingrowth of other elements, decay products in the sample or in the standard. On the other hand, if we have plutonium-239, we have a half-life of 23,000 years. So that ends up being a superior choice, but we don't always have everything that we want. Sometimes we just have to make do with what we have, and that creates problems that we have to consider and take into account. And for some elements, like the higher Z actinides, there's really no practical physical standard, and americium and curium are good examples of that. So we use virtual standards, and what we mean by that is we can take our physical standards. Here we have oxides of thorium, neptunium, and plutonium, and uranium metal, and we can use this CalcZAF program that's freely available and our K ratio data, and we could compute effective counts per second per nanoamp as if all of these elements were measured as metals. And from there, we can predict americium, curium, and so on, and use these values as our standards. One of the things that I found that is perhaps promising for some of these actinides is that we can synthesize some actinide materials into a monazite structured material. And here we have a plutonium monazite in a monazite structure. And this fortunately turned out to be quite homogeneous. We measured 150 points on it, and given this equation here that comes from Goldstein, it had a level of homogeneity of 0.21, which is less than 1. So by the definition of homogeneity presented here, that ends up being a nice standard that we could use for plutonium. And I imagine that we haven't tried it yet, but we could use it for other actinides as well. So this concludes the first part of this presentation, where I'm just talking about the general background. And so to reiterate, the shielding and electronic discrimination lowers the background by a factor of about 100. The quartz 1011 crystal improves actinide and proximal fission product spectral resolution, so that it makes it much easier to perform interference correction. We still suffer in some cases to have accurate mass absorption coefficients, and in some cases they're particularly important. For example, oxide fuel types, and we're going to have new fuel types that we will be looking at with that are in the form of carbides and nitrides, and they will likely suffer from the same kinds of issues. And our correction algorithms still require assessment to determine which ones work best for particular fuel types, since we have really large varieties of fuels that we're now studying. So here's an example of some work that I finished a couple of years ago, and I'm talking about tri-isostructural particles here, fuel particles, also known as TRISO here. And these are fuel particles that are spherical, and they're about 1 millimeter in diameter. The fuel portion is located right here, and in this case, it's a uranium oxycarbide fuel composition. And then there are a series of layers that surround the fuel. So right here we have the buffer. This is a very porous carbon intended to provide a lot of surface area for fission product absorption. We have here what's known as the inner pyrolytic carbon layer, which is a dense carbon layer. The silicon carbon layer is essentially the cladding for this kind of fuel. So it's intended to be the final barrier to keep fission products inside the particle rather than allowing it to go outside the particle. And then on the outside of the silicon carbide, we have an outer pyrolytic carbon layer, and that's in place to physically protect the particle from damage. So if you look at the fuel here, and this is an irradiated particle, you see that pores are quite large in the center, and then as they get towards the edge, they get much finer. So the center part, this fuel part, is called the kernel, and I'm calling this perimeter around the outside with the small porosity, the kernel periphery. And so what I have here are two particles that were irradiated around the same temperature, burn up, those kinds of conditions. But this one here was safety tested, which means that it sat in a furnace at 1600 degrees C for 300 hours, the purpose of which was to look for fission product release. It's an accident simulator of sorts. So I'm going to compare the fission product distribution in these particles and within the particle. And so in each particle, 2 radii were measured. This orange one crosses a gap that occurs during irradiation where this buffer layer delaminates from the IPIC layer. And we have the same thing here. Now, why aren't these radii straight across to form a diameter? Well, they were put in places where we expected to see the most difference between the 2 radii. So if we look here at, we have cesium on this side, strontium on this side. On the top, we have the irradiated particle. On the bottom, we have the safety tested particle. And if we look at cesium, we see the radius here is the one on the gap side of the particle, and the radius here is on the side without the gap. So that's the color scheme in this presentation, is that the gap side is orange or red and the non-gap side is blue. But what we see here with cesium is that it peaks towards the buffer IPIC interface, and then it's symmetrical across the particle. And we see that in both particles. In contrast, strontium is not symmetrically distributed. It occurs in higher concentration in the kernel periphery, as we can see here and here, and it's higher on the non-gap side of the particle. So when I started seeing fission products that behaved non-uniformly, I became curious about how we might examine that more closely or quantify it. And so what I came up with is the idea of taking our particle cross-section and our radial traverses, each comprises maybe 100 points. And what we can do is take the concentration at each measured point, and in combination with the density and the radial distance from the center, we can come up with a mass of a hemicircle with increasing radius, and ultimately we can come up with masses of fission products for the various layers of the particle and the various sides of the particle, the side with a gap and the side without the gap, and we can compare these quantitatively. And so to understand whether this works at all, I did the analysis and the computations and came up with particle masses for these elements in the form of micrograms per particle. And here we have the irradiated particle, and here is the safety tested particle. And here is Origin, which is a predictive program that nuclear engineers use to understand what fission products and what isotopes specifically and what quantity they're going to be producing. And so we're not really interested in uranium per se, but it's in large abundance, and so it should be able to be measured with good precision. It's also more or less confined to remaining in the kernel, so it's homogeneous. And what we see here is that the EPMA over predicts the model by 10% in this particle and 11% in this particle. And so the analytes that came out fairly close are indicated in green, and those include our rare earths, a number of the rare earths, cesium, iodine, barium, palladium. And then there are a few that came out very poorly, xenon, for example, silver, cadmium. In the case of xenon, we understand this because it's lost when you polish the particle, you open up the pores and the gas leaves. Cadmium's in very small quantities and it's overlapped by silver, so the interference corrections there, I think, are hard put to give us a good cadmium value here. And additionally, both cadmium and silver are pretty heterogeneously distributed. And so with 2 radii, we probably don't adequately capture the variation within the particle. But given the number of analytes that measured where the agreement was pretty good, we can then make some comparisons. So if we look here again, our as irradiated particle is blue and the safety tested particle is red. And what we see for these are our layers, from the kernel to the outer pyrolytic carbon layer. And here's cesium with and we're using percent here. So this encompasses all of the cesium in both particles, and the percentage in each layer is indicated by this scale here. And what we see is that cesium accumulates in the buffer, which isn't terribly surprising because it's porous and cesium ends up being volatile, so it just sorbs onto the buffer material. But what we see here is interesting, because what we're showing is that in the as irradiated particle, more of its cesium remains in the kernel and kernel periphery, whereas in the safety tested particle, the cesium has moved more outward toward the outer part of the particle. It's not a surprising outcome, but it's an interesting outcome to be able to quantify and demonstrate. Here we have strontium, and here strontium tends to accumulate in the kernel periphery, in part because the kernel periphery is really enriched in carbon, and strontium forms carbides under these circumstances. But again, we see that we have a relatively large amount of strontium retained in the kernel of our as irradiated particle, and relatively more moved to the kernel periphery in the safety tested particle. neodymium ends up being interesting because the nuclear engineers would say, well, it's conserved. It doesn't go anywhere. It stays right in the kernel. And mostly they're right, but we can see that there's a definite concentration difference or mass difference between the as irradiated particle, which has much more neodymium in the kernel and much less in the kernel periphery, whereas in the safety tested particle, they're even. So again, suggesting that heat and time is allowing for migration of fission products further to the outer layer, confining layers of the particles. Now, one of the things I was interested in is we have these gaps that form between the buffer and the IPIC layer during irradiation, and I wanted to understand how they impact fission product distribution. So what we can see here is the side without the gap is blue and the side with the gap is orange. This is our as irradiated particle. This is the safety tested particle. And what we can see here is that, again, cesium congregates mainly in the buffer, but on the side with the gap, it again extends outward more so than in the side without the gap. And in the safety tested particle, we see that somewhat, but the differences here, well, there are no differences here. So the overall, the differences are much more muted in the safety tested particle. And here we see strontium. Again, it tends to form carbides, and so it accumulates in the kernel periphery. But here we see that it congregates in the kernel periphery much more on the non-gap side than on the side with the gap, and that's true in both of these particles. And so one of the things I had thought about was, does that gap change the thermal conductivity across the particle? Because now you have this void space, and so maybe the side with the gap tends to be hotter. So I employed the assistance of one of our modeling people. And here we have our as irradiated particle and our safety tested particle and our various layers here and temperature here. And so on the side lacking a gap, the temperature from the inside to the outside is fairly uniform. However, on the side with the gap, it's about 15 degrees Kelvin hotter until it gets to the gap, and then it meets the same temperature as the side that has no gap. And we see the same effect over here in the safety tested particle. So indeed, we have different temperatures that may be influencing fission product transport and accelerating it on the side with the gap. So to conclude this little research highlight, the EPMA masses compare favorably with the origin calculated masses for many of the elements, but by no means all of the measured elements. Elements that are heterogeneously distributed tend to be not particularly accurate. The safety testing does cause additional fission product movement outward, which we can quantify using this technique. And the gap formed during irradiation does increase the kernel temperature and the buffer temperature by 15 degrees K in this particular experiment. And that seems to enhance fission product transfer on the particle side that has the gap. So at this point, I can take questions.